Hello, Mr. Ritik Singh. Welcome to
Hello.
YourPedia. Let's start your snap interview on the subject control systems for your BARC, Baba Atomic Research Center, scientist interview preparation, right?
Yes, sir.
Yeah, fine. See, Ritik Singh, tell me what is your favorite topic in control system?
So the damped, undamped dam systems, closed loop, open loop systems, all this I have studied.
Tell me what does it
See,
mean by damping?
uh,
Damping. What what you understood by the word damping?
so damping means when system is it's under its transient state, then slowly it's moves towards its uh, uh, steady state value, and in that journey, the oscillations in the transient response decreases, and that we call as damping in the system. Means it finally settles down to its steady state value.
So, what you told is correct, you feel, about damping, or you want to correct your definition for damping? Ritik Singh,
So I have a general idea. In the proper scientific definition wise, I don't think I'll
tell
go
me
to that part, but
what is the
I have
damping?
an idea
What is
about
the damping of this
damping.
system? What is the damping ratio of this system? I'm giving you one circuit to you. What is the damping ratio of this system? I'm showing
Sir,
one
it's an undamped system.
undamped. Means what?
It's a system, so it's an undamped system.
Means what? What does
So
it mean
the
by
damping
undamped?
ratio would be 1.
Ritik
Means
Singh, what does it
the
mean by undamped? Undamped means what?
so undamped system means the oscillations will go on forever. It will not die down. So we'll get a sine wave in the response. So
Okay, fine.
that's the meaning of undamped system. There are no resistors here for us for the
I'm
system
showing one
to
waveform.
use any damping.
I'm showing one response of a system. Okay. I'm showing one response here.
So can you draw it a little bit down? So
Yeah.
because
Yeah.
there are a lot of pop-ups in my screen and I'm not able to view the complete.
Down you
Yes,
want
sir.
me to go? Okay. Is it
No, sir.
visible now?
Yeah, this question will be
Now?
fine. Sir, little bit downward.
Just a
A
minute.
little bit downward. There are a lot of pop-ups on my screen
Lot
now.
of pop-ups. Okay. I'm resharing my screen.
Okay, sir.
Little bit down. Is it okay now?
It's still loading, sir.
Still loading it is. Okay. I'm drawing one response.
Yes, sir. This portion is fine. Yes.
This is the response. So this system is having positive damping or negative damping?
Positive damping means its oscillation would reduce, but its oscillations are continuously increasing, so that's why I would say negative damping.
Damping is negative. Okay. Now,
Yes, sir.
I'm giving you one circuit. This is a circuit. I'm exciting this one with DC voltage, not AC. I'm exciting this one with DC voltage. Can you draw voltage across capacitor? This is plus minus V. Can you draw voltage across capacitor waveform?
So it will be 2 of V. And 1. Okay, sir. So, visible. So, sir, am I visible to you?
Yes, you are visible. You are visible.
Yes.
Ritik.
So, what I want to say is that uh, the voltage
Take,
across the
take your
capacitor would
take
rise to
your
2V.
copy near to camera so that I'll be able to see your waveform.
Yes,
More
sir.
close, more
Is the
close.
graph visible or should I draw it larger?
Show it to me. So you got one half sinusoidal, right? Half sinusoid, right?
Yes, sir. Uh, and the amplitude, the
Can,
peak value
can
would
you
be 2V.
explain? Can you explain how the circuit is behaving? Initially the inductor is at rest, means no charge in the no energy in the inductor. Capacitor is also not having any energy. Now, can you explain this circuit? What it
Yes,
is
sir. So
happening in the circuit?
uh, initially both do not have any charges. So the capacitor is basically shorted,
Mhm.
and as the capacitor starts to charge, the voltage across the capacitor would start to increase. So, and the similar thing we can see in my graph. This voltage across the capacitor is increasing,
Mhm.
but when it will reach voltage V, then it will not shut off because we also have a inductor in a circuit. So
Okay.
the energy of the inductor would also start flowing to the capacitor.
No, no.
Okay,
Why
and that's why
capacitor?
the whole.
Listen, Ritik, listen. Why
Yes, sir.
capacitor is not stopping at voltage V? You're saying that capacitor starts charging. Yes,
Yes,
capacitor
sir.
charging.
Yes, sir.
Once
Because
it reaches
we.
to
Yeah.
V, according to KVL, once it reaches to V, input voltage is V, voltage across capacitor is also V, and the voltage difference is zero. My question is why capacitor is not stopping at V? Why it is further charging?
Yes, sir. Because since we have an inductor and it's the property of an inductor to resist any sudden change in the current. If
So
like when the
why
capacitor
that current is,
reaches
see,
to.
at that instant of voltage, when voltage across capacitor is V, does the current is zero or non-zero? I repeat,
When voltage across the
when
capacitor
voltage
is
across
V.
capacitor reach to plus V, then the current in
Yes,
the
sir.
inductor is zero or non-zero, positive or negative.
There would be some current in the inductor
How can you say that there
just
would be some
before.
current in the inductor?
So just before the voltage reaches to V in the capacitor voltage reaches to V, there is some current in the inductor. But
How can you say
and
that there is some
like,
non-zero current? What is your expression for the current? See, if you
yes,
want to
sir.
say there is some non-zero
Because
current before voltage across capacitor is capital V, right? For that, there should be an expression. First, tell me what is the expression of the current in the circuit.
voltage across inductor V is equal to L dI by dt. So around is equal to 1 by minus 1 upon dt. So if I have gotten the thing right, I think you are asking about the current across in the inductor, this
No,
expression, right?
see, as it is a series
So the
circuit,
voltage across the
Ritik,
inductor is minus L d across the inductor is minus L di by dt.
no,
And
Ritik,
from here,
listen, Ritik, listen. As it is a series circuit, current in the inductor, current in the capacitor, current through the source, all three must be same, yes or
would
not?
be yes.
What
Yes.
is your expression? I don't want waveform to draw. What is the expression you got for the current?
Expression is mathematical expression. Means QV to CL.
Tell me how to get current expression of this circuit. How to get the current expression of this circuit?
Here we see current expression is V. Okay. So this voltage is equal to minus L dr by dt. Then if I move to Laplace domain, then I can also get the expression. So I can get the current expression by moving to Laplace domain also. So
Fine. Okay, Ritik.
can I do that? Can I do that?
Yeah, please do that. Get me the current expression.
Okay. Let's see. Right. Let's see. Let's see. So basically it's in the left
Tell me orally what is the expression for the current you got. Tell me orally. I don't want any waveform. Tell me orally what is the expression for current
Yes,
you.
sir. That's what I'm showing you right now.
It is not. You tell me orally. I'm asking. You need not to
Okay,
show.
okay. Orally is V upon SL plus 1 upon SC.
See, that is in S domain. Current expression
Yeah.
that must be in time domain. No.
Okay.
What is the idea you are getting if that is in S domain? If it is in frequency domain, we do not get any
It's in
idea.
frequency domain, yes.
You have to convert into time domain. No.
Oh, yes.
Ritik, first listen to the question carefully. Okay.
Okay, sir. Okay.
Fine. Okay. Ritik, let's move to the next question. Ritik.
Okay, sir.
I have a standard second order system.
Okay.
What is the relationship between steady state error and damping of a standard second order system? What is the relationship between damping ratio and error of a standard second order system?
So steady state error is in the system. Then it's as if damping would increase, then steady state error depends on the type of the system. Damping would increase steady state error. So what I have studied is that steady state error depends on the type of the system. So if the type of the system increases,
My
steady
question
state
is,
error
Ritik, I taken a standard second order system. I want the relationship between damping ratio zeta and steady state error of standard second order system.
So I'm not able to recall it right now.
Okay. See, I'm drawing one circuit.
Yes, sir.
Look at the circuit carefully. This system is having some damping zeta, right?
Yes.
If I want to increase zeta, what I have to do with the resistance? Resistance should be decreased or should be increased. I want to increase damping ratio of zeta.
Damping ratio increase means from the basic logical sense, R should be increased.
R should be increased.
If R would be increased, then more loss would be there. So
I want to increase
answer
zeta.
second. Yes, sir, R should be increased.
What is the formula of zeta of this parallel RLC circuit? Zeta formula of parallel RLC. And tell me what is the formula of zeta of series RLC? One is for series RLC and another is for parallel RLC. Tell me, what is the zeta formula of parallel RLC circuit?
Okay, sir. So zeta is equal to 1 upon 2 Q. Okay. Now the parallel is equal to 1 upon C by L. Under root L by C. So for series, it would be R by 2 under root L by C.
For series or parallel, you are saying?
For series.
Okay, for parallel, you tell me. Circuit is parallel
Okay,
circuit, no?
and then for parallel, it would be Q. So we have R under root L by C. Okay. Okay, so P by L under root. Okay, sir. Okay, sir. Now I got it. So see parallel, for parallel, the value of zeta would be 1 upon 2R under root C by X. So according to this relation,
Let me
as
write.
decreases,
1
the
upon
damping ratio should
2R.
increase. So,
Ritik,
yeah,
listen
that would be
carefully.
clear.
1 upon 2R, what is the
Sorry,
formula?
1 upon 2R under root C by L.
C by L.
So here I said it wrong.
Listen, Ritik, listen. Tell me, what are the units of this damping ratio? Units.
Then regarding units,
Damping ratio units.
the resistance unit is ohm, Henry, capacitance would be farad, and that would be Henry. So from basic sense, it ohm, farad to the power 1 by 2, and Henry to the power minus 1 by 2. Putting more general sense. Time constant. From 2 verse. So second inverse.
Huh?
Second inverse.
Second inverse. Okay. Let's go to the next question, Ritik.
Yes,
See,
sir.
I have a system. In fact, I have three systems. Three systems are having poles like this. Those three systems are having poles like this. Three second order systems, in fact. Right? This
Yes,
way,
sir.
I have three systems, and these two poles belongs to one system. These two poles belongs to one system. These two poles belongs to one system. All three systems are going to have some of the variable same, means some of the quantity it is going to have same. All three are going to have same.
Yeah.
What is that quantity? Or what are
So
all the
zeta.
quantities? Maybe one or maybe more than one, right?
Yes, so zeta would be constant there because the
Constant
angle
or
that they are
zeta would
making
be
with the
same.
axis is constant.
Zeta would be same for all three
Yes,
systems.
same, sorry, same.
Okay. Zeta means what?
Damping ratio.
No. Only zeta is the same. Any other things also same for all three systems.
Omega would vary, W1 would vary. And zeta is same. Let me write some expressions here. The response will be confidence. Once again, beta of omega is very dynamics. Beta lifespan, delay time, lifespan, beta of omega. So mean time, beta lifespan, which so sir, no sir, beta would be same.
What
Any
is
other is
what is peak overshoot? Maximum peak overshoot formula?
So, and sir, the peak, what we say, peak was the height of the when the system reaches to its maximum. What's that term? I'm not able to remember right now.
Fine. I'm giving you Ritik Singh. I'm giving you one circuit.
Peak overshoot, sir. Yes, sir. Peak overshoot. The peak overshoot would also be same.
Only peak overshoot, that's all. Any other is also same.
And any other factor, the omega d is equal to omega square. Omega is constant. So, oscillation time, rise time.
Ritik Singh, let's move on to next question. Next question.
Yes, sir. Okay,
this is a circuit I given to you.
Yes,
this
sir.
is the input voltage with variable frequency or F or omega, whatever it is, I'm varying. If my output is voltage across resistor, my output is voltage across resistor, then this particular circuit will behave as which kind of filter?
There is voltage and low pass. High pass, low pass is also. So the
You got
input
my question,
voltage
Ritik?
is varying and we are measuring voltage across a resistor, right?
Yes. Our output voltage is voltage across resistor, then this particular circuit is behaving as what kind of filter?
Okay, so at low frequency, capacitor would get open circuited and high frequency also. Get short circuited and the other thing would get short circuited. मीटर का सही है दो वोल्टेज में करंट तो कुछ जाएगा नहीं इस पे हाई में तो हमको मिल जाएगा लो में इसमें तो हाई फ्रीक्वेंसी में मिल जाएगा लो फ्रीक्वेंसी में चाहिए ओपन सर्किट हो जाएगा this will also get open circuit. Sir, high pass filter.
Yeah. Ritik Singh, let me give you feedback. Okay.
Yes.
Ritik
Yes,
Singh,
sir.
overall, there is a lot of improvement required in your preparation.
Okay, sir.
Okay. I'll explain all the questions what I asked. Okay. I'll explain very clearly
Yes,
all the questions what I asked. If you see this question, it is omega L. This is 1 by omega C. For omega and VR, you take here. For omega equal to 0, this capacitor behaves as open circuit. No current is flowing. Voltage across the resistor is 0. Right. Next, for omega equal to infinity, this is infinity. Omega L, omega into anything. Infinity into anything is infinity. Then also, it is open circuit. Current is 0. Voltage across resistor is 0. Exactly at resonant frequency omega R, this omega L is equal to 1 by omega C magnitude wise, and both are opposite in direction. These two will get cancelled. These two will get short circuit, and voltage across resistor is exactly input voltage. Right? Means,
yes, sir.
Means for low frequency.
It has a band pass filter.
For low frequency, output is 0. For high frequencies, also output is 0. It is like this. It's a band pass filter. These are the actual characteristics, and this is the ideal band pass filter characteristics, right?
Basically, I reached that till that point that there are there's a frequency dependent terms, so I'll get band pass filter. Then because of some performance pressure, I just jumbled all my concepts
and here I given three second order systems with the same.
yes.
You told here zeta is same. Yes, it is correct. What is the MP formula? E power minus pi into zeta.
Minus
root of
pi
one
zeta
minus
upon
zeta
1
square.
minus zeta
Another
square.
thing, right? Number of cycles of oscillations made by the response before it settles is 2 by pi into root of 1 minus zeta square by zeta. This is also exclusively function of zeta. If zeta is same, then number of cycles of the response oscillations made by the response before it settles is going to be same, right? These three things will be same, right? Next.
Yes.
Here, first of all, damping ratio. It is a ratio of two same unit quantities. It should not have any units. Okay.
Oh, yeah, right.
And the units of and the formula of damping ratio of parallel RLC is 1 by 2R into under root of L by C, not C by L. If you take this way, you get this quantity as unitless, Ritik.
Yes, sir, right.
Now, I told I want to increase this zeta, then you decrease this resistance, then zeta will be increased, right?
Yeah, right, sir, yes.
Next. So before to this, I asked a question, what is the relationship between damping ratio zeta and steady state error of a standard second order system, right? What is the open loop transfer function of standard second order system? Omega n square by S into S plus 2 zeta omega n, right?
Yes, sir.
Suppose you are giving a ramp input, then what is you have to find? KV you have to find. KV is limit S tends to 0, S into this OLTF. So if you do that, you're going to get omega n square by 2 zeta omega n gone. You get it as omega n by 2 zeta, right?
Okay, yes, sir.
Now, the steady state error will be ESS is equal to A by KV omega n by 2 zeta. If you take it as unit ramp, A will be 1. So 2 zeta by omega n. If more is the damping ratio, more will be the steady state error. Right?
Yes, sir.
So this is a very small derivation which you must remember. That is the OLTF of standard second order system. That is standard one. You have to remember, right? Ritik.
Yes, sir. Right, sir. I got it.
See, Ritik, the point here in BARC interview is how you are approaching towards the given question is important. And I given you this circuit and I ask you to get the current and voltage across capacitor, right? So you're taking a lot of time for this one. This is LS, this is 1 by CS. If you want current, I of S is equal to V by S. Within no time you get. Or if you remember, you can write that one exactly. LS plus 1 by CS. It is going to be V by S by LCS square plus 1 by CS, right? So you apply partial fractions and you get this one, right?
Okay, this in Laplace domain and then I should
Apply inverse Laplace transform.
Yes, sir.
Apply inverse Laplace transforms, you are going to get the current
Yes,
equation exactly. See, here getting equation is one part. You stopped at getting equation itself. Suppose if you got the current equation, there are a lot of questions possible on the current equation. Why current is increasing? Why current is decreasing? This is mathematical part. See, if you get first a mathematical expression, then I go into the conceptual questions on the same. Right?
Yes, sir.
So my suggestion for you, Ritik, is you start preparing in this direction. See, the direction what I ask questions is completely different the way you prepared, right?
Yes, sir. All the questions that you asked, I was able to figure out from where you are
that's
asking
what
and
is
how.
important for
But,
all students. That is,
yes,
you people know about all these things, these
yeah.
circuits, this formula, everything you learned for your examination preparation. But when it comes to
Yes,
interview, you are not in a position to answer in a proper way because interview is completely different from written examination.
yes,
Okay.
sir.
In interview, see, your approach towards the solution or problem is very important, not just the solution, right?